In this section, you will learn about the fundamental operations of the arrays. Now we get to the heart of working with arrays. There are 5 fundamental operations you will perform on almost any data structure. Traversal. First one is traversal, visiting every element once. Then insertion, adding a new element. Deletion, removing an existing element. Search, finding the position of a given value. And the last one, update, changing the value at a specific index. We will study each one in depth, including the algorithm. And let's start with the traversal operation. So, as you can see as you can understand from the word traversal means processing each element exactly once. Processing could mean printing, summing, or finding maximum, or transforming, etc. Why we need traversal? To compute total or average of all elements, or find the maximum and the minimum values, or display all the values to a user, apply a function to every element, and adding 5 to each score, we need traversal. So the tool we are using for command is for loop. We iterate from index 0 to the index size -1. Usually left to right we are traversing, but you can also traverse from right to left also in an array. Think of a teacher calling attendance. She goes through the list from first student to the last. That's like traversal. She can also go from the bottom of the register and also go to top of the register. Likewise, we can do traversal from the beginning to the end, also from the last element to the first element, using this for loop. Here's the algorithm and the algorithm pseudocode. For I equals 0, which is I means the index, right? I equals 0 to size -1, which is the last element. Output array I. This is the array name we have given, and this is the index. Okay. The time complexity is O(n) here, right? Because we visit each of the n elements once, from 0 to 0th index to size -1 index. So if the array has 1000 elements, how many operations will it do? It has to do 1000 operations, right? And space complexity is O(1). We use only few extra variable like I, regardless of the array size. So no extra array is created here, right? Now let's look at the operation 2, which is insertion. Insertion sounds simple, just add a new element. But with static arrays, there's a catch. Arrays have a fixed capacity. We have two scenarios. Insertion at the end, easy if there is unused space. if the size of the array is less than the capacity, just place the new element at index size and increment its size. It would be easy. Okay, and the second scenario, imagine we have to insert at the beginning of the array or a middle of the array. It's hard because we must shift the elements to make the room for the new element. So let's assume, imagine a shelf of tightly packed books. You have to insert a new book at position 3. You have to push books 3, 4, 5, right, and so on. One slot to the right first, right? Then you place the new book in the empty slot. And we assume the array has unused space. If it's full, insertion is impossible unless we use a dynamic array. We will discuss dynamic array later. Let's look at the visually the insertion. So this is the initial array which is of size 5, and we have 10, 20, 40, 50 and 60. Suppose you need to insert a value 30 at index 2. So what you need to do? You have to shift these elements to the right? In order to make the room for 30 here, you have to move these values, right? Then it will be like this. Then we have to insert the index 30 value at index 2, right? The result would be size 6 array. Okay, so it's important when shifting we must loop from the end backward to avoid overwriting data. If we loop from left to right, we would lose values. Okay, suppose we shift 40 to 50 initially. At the index we shift 40 to here, so this value will be replaced with 40, so it becomes overwritten, right? So we need to do it from here, right? Now let's look at the insertion algorithm. Here's the algorithm with precondition. Size should be less than the capacity. Okay, and also the k is the valid position, and you can insert at the end where k equals size, right? And the pseudocode is this. If size equals capacity, what will happen? The array is full, right? So we can't insert new values. For I equals size minus 1 and down to k, it will become, we have to shift these elements to the right, like in previous example. Okay, and the array kth index value will become is the we have to replace that value, right? Insert that value. and the size of the array becomes size plus 1, right? So end the process. Just like in previous example, this is the algorithm for the insertion. Okay. Now let's look at how efficient insertion is. In best case, insertion at the end, right? So there's no shifting needed, so the complexity becomes O1, which is a constant time. Suppose we have to insert an element at the beginning of the array. So we need to, if the size of the array has n elements, we have to shift all the n elements. So the complexity becomes O(n), which has a linear time, right? Think about insertion at a random position. On average, we have to about shift like n by 2 elements. In big notation, we drop the constant, so the complexity becomes, if n divided by 2, the complexity becomes, if we drop the constant, it becomes O(n), right? And space complexity becomes O1. We are inserting in a place, so there's no extra array needed. It becomes O1. So we can say insertion is cheap at the end but expensive at the beginning or middle. If you need frequent insertions at arbitrary positions, an array might not be the best choice. Consider a linked list. We will be discussing it later, right? Now we have covered the traversal and the insertion. You should now understand how to traverse an array and its O(n) time complexity, and why insertion requires shifting, how to implement insertion at a given position, and the best case, worst case and average case complexities of insertion. In next section we will cover release and search and update. Okay.